Have you ever looked up at the night sky, filled with countless stars, and wondered where it all came from? Not just the stars and galaxies, but everything, the very space they occupy, and the time that ticks by, measuring their ancient dance. Where did time and space themselves begin? It's a question that has puzzled humanity for millennia. A cosmic mystery that takes us to the very edge of existence. Today, we're embarking on an incredible journey. A journey back to the beginning of everything. Let's explore the birth of time and space. To understand the beginning, we first need to grasp what we're talking about. What exactly are space and time? For centuries, we thought of them as a fixed, unchanging stage on which the drama of the universe unfolds. Space was just an empty box, and time was a universal clock, ticking at the same rate for everyone, everywhere. This was the world as described by Isaac Newton. It's intuitive. It makes sense in our daily lives. But as we'll see, the universe is far stranger and more wonderful than that. The big shift in our understanding came just over 100 years ago, thanks to a brilliant mind named Albert Einstein. His theories of relativity completely revolutionized our concept of reality. Einstein showed us that space and time are not separate entities, but are woven together into a single, dynamic fabric. And this fabric isn't flat and rigid. It can be bent, stretched, and warped by mass and energy. Imagine placing a heavy bowling ball on a trampoline. It creates a dip, a curve, in the surface. According to Einstein, this is exactly what massive objects like planets and stars do to space, and what we perceive as gravity is simply objects following these curves. This idea is mind-bending, but it's been proven time and time again. GPS satellites in orbit have to account for the fact that time literally runs faster for them than for us on the ground, a direct consequence of space-time being warped by Earth's gravity. So, space isn't an empty stage. It's an active participant. And time isn't a universal clock. It's relative. Its pace, depending on your motion and your position in a gravitational field. This dynamic, flexible space-time is the arena where a cosmic story begins. So, if space-time can be warped and stretched, what happens if we rewind the clock? We see galaxies rushing away from us in every direction, which means that in the past, everything must have been closer together. If we go back far enough, everything we see, all the stars, galaxies, all the matter and energy in the universe must have been concentrated into an unimaginably hot, dense point. This is the core idea of the Big Bang Theory. It's not an explosion in space. It's the explosion asterisk of asterisk space itself. Let's rewind to that first infinitesimal moment. We're talking about 13.8 billion years ago. At this point, all four fundamental forces of nature, electromagnetism, and the strong and weak nuclear forces were likely unified into a single super. The entire observable universe was smaller than an atom, a point of infinite density and temperature known as a singularity. In T-state, our current laws of physics break down. The concepts of space and time as we know them probably didn't even exist. It's a realm so extreme that it's beyond our current comprehension. A true before the beginning. Then, it happened. In the tiniest fraction of a second, the universe underwent a period of exponential expansion called cosmic inflation. Imagine a balloon being inflated from the size of a marble to the size of the Earth in less than the blink of an eye. This is what happened to space itself. It expanded faster than the speed of light, smoothing out any initial wrinkles and creating the vast, relatively uniform universe we see today. This incredible burst of growth is what gave us the sheer scale of our cosmos. It's the bang and the Big Bang. As space expanded, it also cooled. The unified forces began to freeze out and separate from each other, one by one. The universe was a sizzling soup of fundamental particles, quarks, electrons, photons, flitting in and out of existence. It was a chaotic, energetic plasma, so hot and dense that light couldn't travel freely. For about 380,000 years, the cosmos was an opaque fog. If you could have been there, you wouldn't have seen a thing. Then, a crucial milestone was reached. The universe cooled enough for protons and electrons to combine and form the first stable atoms, mostly hydrogen and helium. Suddenly, The fog cleared. Light was finally free to travel across the cosmos. This first light is something we can still detect today. It's called the Cosmic Microwave Background, or CMB. It's the faint afterglow of creation, a baby picture of the universe, and one of the strongest pieces of evidence for the Big Bang. When you see static on an old television set, a tiny fraction of that snow is interference from the birth of the universe. With the fog lifted, the stage was set for the next act. Gravity, ever persistent, began to pull the newly formed hydrogen and helium gas into massive clouds. Over millions of years, these clouds grew denser and hotter at their cores, until the pressure and temperature were so immense that nuclear fusion ignited. The first stars were born, shining light into the cosmic darkness. These were not like our sun. They were colossal, blue giants, living fast and dying young, ending their lives in spectacular supernova explosions. These explosions were fundamentally important. They forged heavier elements inside their fiery cores: carbon, oxygen, iron, all the elements necessary for planets and, eventually, for life. These elements were then scattered across space, seeding the next generation of stars and solar systems. Our own solar system, our planet, and even the atoms in your body were forged in the hearts of these long-dead stars. As the great astronomer Carl Sagan famously said, "We are made of stars." So, we've traveled from a point of unknown physics, through a period of incredible expansion, to the formation of the first atoms, and the lighting of the first stars. We've witnessed the birth of the universe, the emergence of space as a vast, expanding fabric, and the beginning of time's forward march. But this journey also leaves us with profound questions. What came asterisk? Before asterisk the Big Bang? Was there a before? Since time itself began with the Big Bang, the question might not even make sense. It's like asking what's north of the North Pole. Some theories, like string theory or loop quantum gravity, try to peek beyond this wall. They propose ideas like a cyclical universe that expands and contracts forever, or a multiverse with countless other universes being born from a quantum foam. These are ideas on the frontier of science, pushing the limits of our imagination and our mathematics. We don't have the answers yet, but that's the beauty of science. The quest for knowledge never ends. From a single incomprehensible point to a cosmos teeming with 1 trillion galaxies, the story of the birth of time and space is the ultimate origin story. It's a story of change, of transformation, and of the incredible power of the laws of nature. The next time you look at the stars, remember this journey. You are not just looking at distant lights. You are looking back in time, witnessing the echoes of creation itself. You are a part of a 13.8 billion-year-old story, a conscious piece of the universe trying to understand itself. Have you ever looked up at the night sky, at your own hand, or at the device you're watching this on, and wondered, where did all this stuff come from? It seems like a simple question, but the answer is one of the most epic stories. A story that starts in the fiery heart of the Big Bang and stretches across billions of years. Today, we're going on an incredible journey to uncover the origin of everything, the formation of matter itself. It all begins nearly 13.8 billion years ago. Forget stars. Forget planets. Forget even atoms. In the first fraction of a second after the Big Bang, the universe was an unimaginably hot, dense soup of pure energy. Think of a point smaller than a pinhead containing all the energy that would ever exist. It was a chaotic, sizzling plasma of fundamental particles popping in and out of existence. These weren't the protons and neutrons we know today, but even more basic ingredients. Quarks and like electrons, along with force-carrying particles. The universe was expanding and cooling at an astronomical rate, and this cooling was the key. As the universe cooled from trillions of degrees, something amazing happened. It's like when steam cools and condenses into water. The fundamental forces of nature we know to electromagnetism, and the strong and weak nuclear forces began to freeze out, separating from a single unified force. This critical moment set the stage for the next incredible step. Within the first microsecond, the universe cooled enough for quarks to finally group together. In a frantic cosmic dance, they combined in threes to form the very first protons and neutrons, the building blocks of atomic nuclei. For the first time, the universe had substance, but it was still a chaotic, hot plasma. Protons, neutrons, and electrons were still zipping around freely. Too energetic to settle down. For the next few minutes, the entire universe was like the core of a giant star. In a process called BigBang nucleosynthesis, protons and neutrons fused together. They formed the nuclei of the simplest elements. Mostly hydrogen, a good amount of helium, and tiny, trace amounts of lithium. Imagine, the elemental recipe for the entire cosmos was written in just the first few minutes of its existence. But here's the catch. Even though the nuclei were formed, the universe was still too hot for them to capture electrons and become stable atoms. It was a scorching, opaque fog of charged particles. Light couldn't travel freely. It was constantly scattered, like light in a dense fog. The universe was dark. This cosmic dark age lasted for about 380,000 years. It might sound like a long time, but on a cosmic scale, it's just the blink of an eye. During this period, the universe continued to expand and cool. Finally, it reached a tipping point, cooling to about 3,000 degrees Celsius. At this temperature, the frantic energy of the electrons dropped enough for the positively charged nuclei of hydrogen and helium to finally capture them, forming the first neutral atoms. This event is called recombination, and it changed everything. Suddenly, the universe became transparent. Photons, particles of light, were finally free to travel unimpeded through space. This very first light is something we can still detect today as the cosmic microwave background radiation of fame. Beautiful afterglow of creation. Now that we have atoms, where do the stars and galaxies come from? Well, the early universe wasn't perfectly uniform. There were tiny, minuscule fluctuations in density in that primordial soup. Gravity, the patient architect of the cosmos, went to work on these tiny imperfections. Over millions of years, gravity pulled the slightly denser regions of hydrogen and helium gas together. These clouds grew larger and larger, denser and denser, until the pressure and temperature at their cores became so immense that a new fire was lit. Nuclear fusion. The first star is ignited, breaking the cosmic dark age and flooding the universe with light once more. These first stars were giants, hundreds of times more massive than our sun. They burned through their fuel incredibly quickly, living fast and dying young in spectacular explosions called supernova. But their death was not an end. It was a new beginning. Inside the fiery furnaces of these stars and during their explosive deaths, the simple elements of hydrogen and helium were fused into heavier elements: carbon, oxygen, nitrogen. Iron, all the elements essential for life, as we know it, were forged in these stellar factories and scattered across the cosmos. The stardust, this enriched gas and dust, then formed new clouds. These new clouds, seeded with heavier elements, collapsed under gravity to form the next generation of stars and planetary systems, including our own. The dust and rock in the disk of gas surrounding our young sun clumped together, forming planets, asteroids, and comets. Earth was born from this cosmic recycling program. The iron in your blood, the calcium in your bones, the carbon that forms the basis of all life on our planet. Every single atom in your body that exhumed hydrogen was forged in the heart of a long-dead star. As the famous astronomer Carl Sagan said, "We are made of star stuff." From a singularity of pure energy to a chaotic soup of quarks, from the first atoms to the birth of stars, and from the explosive death of those stars to the formation of our planet and ourselves. The story of matter is the story of cosmic evil. It's a story of creation, destruction, and recycling on the grandest scale imaginable. So, the next time you look at the world around you, remember this incredible journey. You are not just living in the universe is living in you. Every atom has a story that stretches back to the very beginning of time. And the best part, the story isn't over. Stars are still being born, new elements are still being forged, and the universe continues to evolve in ways we are only just beginning to understand. Intro music begins, then fades to a soft, wondrous background track. Have you ever looked up at the night sky, studded with countless stars, and wondered where it all came from? It's a question that has captivated humanity for millennia. Today, we're embarking on an epic journey back in time, to witness one of the most magnificent events in cosmic history, the rise of galaxies. Right after the Big Bang, the universe was a very different place. It was a hot, dense soup of particles and energy, expanding and cooling rapidly. There were no stars, no planets, and certainly no galaxies. For the first few 100,000 years, it was a dark, foggy cosmos where light couldn't travel freely. Then, about 380,000 years after the Big Bang, something amazing happened. The universe cooled enough for protons and electrons to combine and form the first atoms, mostly hydrogen and helium. This event, known as recombination, cleared the cosmic fog. For the first time, light could travel across the universe. This ancient light is what we now see as the cosmic microwave background radiation, the afterglow of the Big Bang itself. But even with light, the universe was still mostly dark and empty. It was what astronomers call the cosmic dark ages. So, how did we get from this vast, dark emptiness to the brilliant spiral and elliptical galaxies we see today? The secret lies in something incredibly subtle. Tiny, almost imperceptible variations in the density of matter. Think of it like this. The early universe wasn't perfectly smooth. Some regions were just a tiny fraction denser than others. And in the universe, gravity is king. These slightly denser regions had a bit more gravitational pull, and over millions of years, they began to attract more and more matter from their surroundings. The rich got richer, gravitationally speaking. These initial clumps of matter were the seeds of everything to come. They were mostly made of that primordial hydrogen and helium, plus a mysterious, invisible substance we call dark matter. In fact, dark matter played the lead role. It makes up about 85% of all matter in the universe. And, because it doesn't interact with light, it could start clumping together even before recombination, providing the gravitational scaffolding for galaxies to form. Slowly but surely, these clumps grew. Over hundreds of millions of years, gravity pulled them into massive clouds of gas, collapsing under their own weight. As the gas compressed, the pressure and temperature at the centers of these clouds skyrocketed. Eventually, it became hot and dense enough to ignite nuclear fusion. The very first stars were born. These first-generation stars, known as population 3 stars, were unlike any we see today. They were giants, hundreds of times more massive than our sun, and they burned incredibly hot and bright. But their lives were short and spectacular. They blazed for only a few million years before ending in colossal supernova explosions. These explosions were crucial. They scattered heavier elements, the carbon, oxygen, and iron that are essential for planets and for life, out into the cosmos. These elements enriched the surrounding gas clouds, paving the way for the next generation of stars. These early stars didn't form in isolation. They were born in clusters, held together by gravity, and these clusters of stars and gas began to merge. Think of it as a cosmic dance of gravitational attraction. Small collections of stars, which we call proto-galaxies, pulled each other in. They collided and merged, growing larger and larger over time. This process, called hierarchical merging, is the leading theory for how large galaxies like our own Milky Way were built. It wasn't a single, neat event, but a chaotic and continuous process of cosmic construction spanning billions of years. Smaller dwarf galaxies were gobbled up by larger ones, adding their stars, gas, and dark matter to the growing metropolis. Through powerful telescopes like the Hubble and James Webb Space Telescopes, we can actually see this process happening. By looking deep into space, we are looking back in time. We can see these distant, young galaxies, often clumpy, irregular, and in the middle of dramatic collisions. They are the building blocks of the grand structures we observe in our cosmic neighborhood. Over time, these mergers and the relentless pull of gravity shape the galaxies into the forms we recognize. Some, through a violent history of mergers, settled into huge, roundish balls of old stars, which we call elliptical galaxies. Others, which had a more gentle evolution and retained their spin, flattened out into magnificent spinning disks with beautiful spiral arms, just like our Milky Way. And at the heart of nearly every large galaxy, including our own, lurks a supermassive black hole. It is a bit of a chicken and egg situation. Weary still, trying to figure out which came first, the galaxy or its black hole. But it is clear they grow together and influence each other. It's evolution in a profound cosmic partnership. So, when you look up at that vast night sky, remember what you're seeing. Each point of light, each fuzzy patch, is part of a story that has been unfolding for over 13 billion years. A story of gravity, dark matter, and countless generations of stars. From a dark, uniform soup, the universe has built a breathtakingly complex and beautiful tapestry of galaxies. And we, on our small planet, orbiting an ordinary star in the suburbs of the Milky Way, are lucky enough to be here to witness it and to wonder about it all. Have you ever looked up at the night sky and wondered what those twinkling lights really are? They're not just tiny diamonds scattered across a velvet cloth. They are colossal, burning balls of gas, each with its own incredible life story. Today, we're going on an epic journey through space and time to witness the spectacular life and death of stars. So, where does a star begin? It all starts in a place that looks like a cosmic cloud, a vast, cold expanse of gas and dust, called a stellar nebula. Imagine a cloud so enormous, it stretches for light. Within these nebulae, gravity is the master architect. It slowly pulls clumps of gas and dust together. As these clumps grow denser, gravity squeezes them tighter and tighter. The pressure and temperature at the core start to skyrocket, climbing to millions of degrees. When it gets hot enough, something magical happens. Nuclear fusion ignites. This is the moment a star is born, a protostar leveling up to become a main sequence star, just like our very own sun. This main sequence phase is the longest and most stable part of a star's life. It's like the star's adulthood. For billions of years, it will peacefully fuse hydrogen atoms into helium in its core, releasing an immense amount of energy in the process. This energy, which we see as light and feel as heat, is what pushes outward, perfectly balancing the inward pull of gravity. Our sun is currently in the middle of its main sequence life, and it's got about another 5 billion years of fuel in the tank. But not all stars are the same. A star's mass is the single most important factor, determining its entire life path. Think of it this way. The more massive a star is, the faster it burns through its fuel. It lives fast and dies young. Less massive stars, on the other hand, are more frugal. They sip their hydrogen fuel slowly and can live for tens or even hundreds of billions of years. But what happens when the fuel starts to run out? This is where the story takes a dramatic turn. For an average star like our sun, once the hydrogen in its core is depleted, gravity begins to win the battle. The core contracts and heats up even more. This extra heat causes the star's outer layers to expand dramatically, puffing up like a giant balloon. The star transforms into a red giant. It becomes hundreds of times larger, and despite its cooler surface temperature giving it a reddish hue, it's actually more luminous than ever. In about 5 billion years, our sun will become a red giant, expanding so much it will likely swallow Mercury, Venus, and possibly even Earth. It's a sobering thought, isn't it? During this phase, the core becomes hot enough to start fusing helium into heavier elements, like carbon. But this new phase of fusion doesn't last forever. For a star like the sun, it doesn't have enough mass to ignite the fusion of heavier elements beyond carbon. So, after the helium is gone, the star's life is essentially over. The outer layers drift away into space, creating a beautiful, glowing shell of gas, called a planetary nebula. These aren't related to planets at all. They just looked a bit like them to early astronomers. What's left behind at the center is the star's hot, dense core, a tiny, glowing ember called a white dwarf. A white dwarf is incredibly dense. A single teaspoon of its material would weigh several tons on Earth. It no longer produces any new energy. It has just a cooling cosmic remnant that will slowly fade over trillions of years until it becomes a cold, dark black dwarf. A quiet, peaceful end to a once brilliant star. But for stars that are much more massive than our sun, at least 8 times the stay, and is anything but quiet. It is the most violent and spectacular event in the universe. These massive stars live short, furious lives. When they run out of hydrogen, they don't just become red giants. They become red supergiants, like Betelgeuse in the Orion constellation. Their immense gravity allows their cores to get hot enough to fuse heavier and heavier elements, going from helium to carbon, then to neon, oxygen, silicon, and finally, to iron. But here's the critical part. Fusing iron doesn't release energy. It consumes Italiano. This is the point of no return. With its energy source gone, the star's core collapses under its own tremendous gravity in a fraction of a second. This catastrophic collapse triggers a massive shock wave that blasts the star's outer layers into space in a titanic explosion known as a supernova. For a few weeks, a single supernova can outshine an entire galaxy, releasing more energy than our sun will in its entire 10 billion-year lifetime. This explosion is not just destructive, it's also creative. The intense energy of the supernova forges all the elements heavier than iron, gold, silver, platinum, uranium, and scatters them across the cosmos. Every bit of gold in your jewelry, every bit of calcium in your bones, was forged in the heart of an exploding star billions of years ago. We are, quite literally, made of stardust. What happens after the supernova? It depends on the mass of the star's remaining core. If the core is between about 1.4 and 3 times the mass of our sun, the collapse is so intense that it crushes protons and electrons together to form neutrons. The result is a neutron star, one of the densest objects in the universe. Imagine a city-sized sphere with more mass than our sun. They are so dense that a sugar cube-sized amount of neutron star material would weigh as much as all of humanity combined. Some neutron stars spin rapidly and emit beams of radiation, which we observe as pulsars like cosmic lighthouses blinking across the galaxy. But what if the core is even more massive, more than 3 times the mass of the sun? Then not even the neutrons can withstand the force of gravity. The core collapses completely, infinitely, into a single point of zero volume, an infinite density. Singularity. This creates a region of spacetime where gravity is so strong that nothing, not even light, can escape. A black hole is born. Black holes are the universe's ultimate mystery boxers. They warp the fabric of space and time around them, swallowing anything that gets too close. They are the final, silent gravestones of the most massive stars in the cosmos. So from a gentle cloud of dust to a brilliant main sequence star, to a bloated red giant or a raging supergiant, and finally to a quiet white dwarf, a dense neutron star, or an enigmatic black hole. The life of a star is a cycle of creation and destruction. The very elements forged in their fiery hearts and scattered in their explosive deaths become the building blocks for new stars, new planets, and even new life. The next time you gaze at the night sky, remember that you're not just looking at distant lights. You're looking at the grand, cosmic story of our universe, a story of birth, life, and death, written in fire across the heavens. And in a very real way, you are a part of that story. Have you ever looked up at the night sky and wondered, how did we get here? Not just us, but everything. Our planet, our home, Earth. It's a story that unfolds over billions of years, a cosmic drama of fire, ice, and incredible transformation. Today, we're going to travel back in time, all the way to the very beginning, to witness the incredible birth of our world. Our story starts about 4.6 billion years ago. Imagine a vast, swirling cloud of gas and dust, a giant cosmic nursery called a solar nebula. This wasn't just any cloud. It was the leftover material from the birth of our star, the sun. For millions of years, this cloud just drifted. But then, something gave it a nudge, perhaps a shockwave from a nearby exploding star. A supernova. This cosmic push set everything in motion. Gravity, the silent architect of the universe, began to pull the dust and gas together. The cloud started to spin, faster and faster, flattening into a disk like a potter shaping clay on a wheel. At the very center, where the pressure and temperature skyrocketed, our sun ignited, bursting into life. But what about the rest of the material? The stuff spinning in the outer parts of the disk? That's where things get really interesting for us. In this spinning disk, tiny dust grains started sticking together, a process called accretion. Think of it like a snowball rolling downhill, getting bigger and bigger. These clumps grew from pebbles to rocks, then to boulders, and eventually into massive bodies called planetesimals, some several miles across. It was a chaotic and violent time, a cosmic demolition derby. These planetesimals constantly crashed into each other, either shattering into smaller pieces or merging to form even larger objects. Over millions of years of these cosmic collisions, a few big winners emerged. One of these was a young, molten ball of rock that would one day become our Earth. But the early Earth was nothing like the blue and green marble we know today. It was a hellish landscape, a glowing sphere of molten lava with a surface temperature hot enough to melt rock. There was no water, no air, just a fiery, bubbling cauldron bombarded by a constant hail of asteroids and comets. Then, in a truly cataclysmic event, our young Earth collided with a Mars-sized protoplanet named Vea. This wasn't just a bump, it was a planet-shattering impact. The collision was so immense, it blasted a massive amount of molten rock from both bodies into orbit around Earth. Gravity worked its magic once again, pulling this debris together. Over time, this ring of molten rock coalesced to form our constant celestial companion, the Moon. This giant impact hypothesis is the leading theory for how the Moon was formed, and it explains why the Moon's composition is so similar to Earth's crust. After this monumental impact, Earth began to slowly cool. The heavier elements, like iron and nickel, sank towards the center, forming the planet's dense core. This process, known as differentiation, created the layers we know today: the core, the mantle, and the crust. The formation of the iron core was crucial, as its motion generates Earth's magnetic field. This magnetic field acts like an invisible shield, protecting us from harmful solar radiation. Without it, life on Earth would be impossible. As the planet continued to cool over hundreds of millions of years, a solid crust began to form on the surface. But the bombardment wasn't over. Comets and asteroids, which are essentially giant, icy space rocks, continued to crash into Earth. This period is known as the Late Heavy Bombardment. While destructive, these impacts delivered a precious gift: water. As these icy bodies vaporized on impact, they released vast amounts of water vapor into the atmosphere. At the same time, intense volcanic activity was spewing gases from Earth's interior gases, like water vapor, carbon dioxide, and nitrogen. A primitive atmosphere began to form. As the planet cooled further, the water vapor in this thick, soupy atmosphere condensed and fell as rain. It didn't just rain for a day or a week. It rained for millions of years. This relentless downpour filled the basins and craters, forming the first oceans. Picture it: a world with a single, massive ocean under a thick, cloudy sky. Continents as we know them didn't exist yet. The first land masses were likely small volcanic islands, poking out of the global sea. Beneath the waves, a new chapter was about to begin. The stage was set. The ingredients were all there: water, a stable environment protected by a magnetic field, and a rich cocktail of chemicals. In these ancient oceans, in the deep, dark, hydrothermal vents, or perhaps in shallow, sunlit pools, the first sparks of life ignited. But that's a story for another time. From a swirling cloud of dust to a molten ball of fire, and finally to a water world poised for life. The creation of Earth is a tale of cosmic chance, violent collisions, and incredible transformation. Every time you feel the solid ground beneath your feet or see the waves crash upon the shore, you are witnessing the legacy of a 4.6 billion-year-old journey. It's a reminder that we live on a truly special and dynamic world, a product of the cosmos itself. And wondered, how did all of this begin? How did a barren, rocky planet transform into the vibrant world teeming with life that we see today? It's one of the biggest questions humanity has ever asked. And the answer is a story more incredible than any fiction. It's the story of evolution. So, grab a seat, get comfortable, and let's journey back in time billions of years. Uncover the epic tale of life on Earth. Our story begins about 4.5 billion years ago, with a young, fiery Earth. It was a chaotic and hostile place, constantly bombarded by asteroids and comets, with a toxic atmosphere and oceans of molten rock. It was hardly a welcoming home. But somewhere in this primordial soup, perhaps in the warm, shallow waters or near hydrothermal vents, deep in the ocean, something extraordinary happened. Simple, non-living chemical compounds began to organize themselves. Over immense spans of time, these molecules formed self-replicating structures. This was the spark. This was the birth of the very first, incredibly simple life forms. We call this theoretical ancestor Luca, the last universal common ancestor. It wasn't an animal or a plant. It was likely a single-celled organism, a microscopic speck floating in the ancient seas. For nearly 1 billion years, life remained this simple. But don't underestimate these tiny pioneers te werebusi. One group, the cyanobacteria, developed a revolutionary trick: photosynthesis. They learned to harness the power of the sun, and in doing so, they began to release a waste product. That waste product was oxygen. This event, known as the Great Oxidation Event, was a total game changer. For many of the early life forms, oxygen was toxic, leading to a mass extinction. But for others, it was an incredible opportunity. This new, energy-rich atmosphere paved the way for more complex life. Cells started to develop specialized compartments, or organelles, becoming what we call That's the type of cell that makes up you, me, every animal, plant, and fungus on the planet. Some of these cells even started working together, forming the first multicellular organisms. Life was no longer just a collection of single cells. It was becoming a team sport. Fast forward to about 540 million years ago, and we hit one of the most explosive chapters in our story: the Cambrian explosion. In what seems like a geological blink of an eye, the oceans burst with an incredible diversity of complex animal life. We see the first creatures with shells, exoskeletons, legs, and primitive eyes, ancestors of insects, crustaceans, and even vertebrate animals, with backbones made their debut. It was a wild biological experiment, with evolution trying out all sorts of new body plans. Many of these strange and wonderful creatures, like T5 have long since vanished, but their existence shows the sheer creative power of natural selection. But life wasn't content to stay in the water. The land was a vast, open frontier, and life was ready to conquer it. First came the plants. Small, moss-like organisms started creeping onto the shores, followed by ferns and eventually towering forests. They transformed the landscape and created new habitats. Soon after, animals followed. Arthropods, like ancient millipedes and scorpion-like creatures, were among the first to venture ashore. Then came the amphibians, evolving from lobe-finned fish, learning to breathe air and walk on land, though still tied to the water to lay their eggs. This was a monumental step, setting the stage for the age of reptiles. And what an age it was. The Mesozoic era is famously known as the Age of Dinosaurs. For over 150 million years, these magnificent creatures dominated the planet. From the colossal, plant-eating sauropods to the fearsome Tyrannosaurus rex, they diversified into an astonishing array of shapes and sizes. They ruled the land, the sea, and the air. While dinosaurs reigned supreme, another group of animals was quietly biding its time in the shadows. The mammals. They were small, often nocturnal, but they were adaptable and resilient, and their moment was coming. Then, 66 million years ago, disaster struck. A massive asteroid, estimated to be 6 miles wide, slammed into the Earth near modern-day Mexico. The impact triggered a global catastrophe, a long winter that blocked out the sun, causing plants to die and ecosystems to collapse. The dinosaurs, along with about 75% of all species on Earth, were wiped out. It was a devastating mass extinction. But every ending is also a new beginning. With the giant reptiles gone, the surviving mammals found a world of opportunity. This brings us to the Cenozoic era, the age of mammals. In the wake of the extinction, mammals diversified rapidly, filling the ecological niches left vacant by the dinosaurs. Whales returned to the oceans, bats took to the skies, and on the plains of Africa, a particular group of primates began a remarkable journey. They started spending more time on the ground, developing the ability to walk upright on two legs. This freed up their hands for carrying food and making tools. Their brains grew larger and more complex. These were our ancestors, the early hominins, from species like Australopithecus to Homo habilis, the toolmaker, and Homo erectus, who mastered fire and migrated out of Africa. Our family tree grew and branched. Finally, our own species, Homo sapiens, emerged around 300,000 years ago with our advanced cognitive abilities, capacity for language, and complex social structures. We spread across the globe, adapting to every environment we encountered, from painting in caves to building skyscrapers and exploring space. Our journey is the latest, and perhaps most dramatic, chapter in the epic of evolution. So, from a single cell in a primordial ocean to the billions of species alive today, the story of life is a testament to resilience, adaptation, and the incredible power of time. It's a story that's still being written every single day, in every living thing. It's our story, and it connects every one of us to the very beginning of life on Earth. Have you ever looked up at the night sky? Truly looked, and felt a profound sense of wonder, a sense of smallness, but also of connection. It's a feeling that has captivated humanity for millennia. We've gazed at those distant points of light and asked the biggest questions. Are we alone? What is our place in this vast, sprawling cosmos? And perhaps most importantly, where are we going? Today, we're embarking on a journey not just through space, but through time. We're going to explore the grand, cosmic future of humanity. This isn't just about rockets and far-off planets. It's about the very essence of what it means to be human in a universe far larger and older than we can truly comprehend. For nearly all of our history, Earth has been our cradle. It's the only home we've ever known. But as the saying goes, one cannot remain in the cradle forever. The same drive for exploration that pushed our ancestors across oceans is now pushing us towards the stars. The first steps have already been taken. We've walked on the moon, sent rovers to Mars, and our probes have visited every planet in our solar system, even venturing into the interstellar medium beyond. But these are just the baby steps. The next giant leap involves establishing a permanent human presence beyond Earth. Imagine a thriving city on Mars, its inhabitants looking up at a tiny blue dot in their sky. Our ancestral home, imagine bases on the moon, mining for resources like helium-3 to power a new generation of fusion reactors back on Earth. This isn't science fiction anymore. It's the engineering challenge of our time. Companies and space agencies around the world are actively working on the technologies to make this a reality within our lifetimes. Living on Mars or the moon would be a monumental achievement, a testament to our ingenuity and resilience. But why stop there? Our solar system is a treasure trove of worlds. The moons of Jupiter and Saturn, like Europa and Enceladus, hide vast liquid water oceans beneath their icy shells. Could life exist there? Exploring them could answer one of the most fundamental questions we've ever asked. Further out, the asteroid belt offers unimaginable mineral wealth, resources that could fuel our expansion and reduce the strain on our home planet. Becoming a multiplanetary species isn't just about adventure. It's an insurance policy. Life on Earth is precious, but it's also fragile. A single catastrophic event, an asteroid impact, a supervolcano, or even a self-inflicted disaster could end our story prematurely. By spreading out among the stars, we guarantee the survival of human consciousness, art, science, and culture. We become custodians of a legacy that transcends a single world. But even our solar system is just one tiny corner of the Milky Way galaxy. The true cosmic future of humanity lies in interstellar travel. The distances are staggering, almost beyond imagination. Our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. With our current technology, it would take tens of thousands of years to get there. So, how do we cross this immense void? This is where our vision must stretch. Scientists are exploring radical new concepts for propulsion. Imagine vast, ultra-thin light sails, pushed by powerful lasers from Earth. accelerating tiny probes to a significant fraction of the speed of light. These could reach nearby stars within a human lifetime. Or consider fusion rockets, harnessing the power of the stars themselves to propel massive generation ships on centuries-long voyages, with entire communities living and dying on board. Their descendants being the first to arrive at a new star system. And then there's the more speculative, mind-bending physics. Could we one day harness the fabric of space-time itself? Concepts like wormholes or warp drives, while purely theoretical for now, remind us that our understanding of the universe is still in its infancy. What seems impossible today might be tomorrow's breakthrough. The history of science is filled with such leaps of imagination. As we venture further, we might encounter another profound question. Are we alone? The galaxy is home to hundreds of billions of stars, and we now know that most of them have planets. Statistically, it seems almost improbable that Earth is the only world to have given rise to life, and perhaps intelligence. What would first contact look like? Would we find microbial life on an alien moon? Or would we intercept a signal from a civilization millions of years older than our own? The implications are staggering. It would reshape our philosophy, our religions, and our understanding of our own place in the universe. It would be the single most important discovery in human history. Maybe we wouldn't find anyone, and the realization that this vast cosmos is silent would be just as profound, placing an even greater responsibility on us as the sole bearers of consciousness in our galactic neighborhood. But let's bring it back. This grand future isn't just about technology. It's about us. How will humanity itself change as we spread into the cosmos? Those who live on Mars, with its lower gravity, might evolve differently over generations. Cultures will diverge, creating new traditions, new art, and new ways of seeing the universe, all born from the shared human spirit, but shaped by new worlds. We may even transcend our biological limitations. The challenges of long-duration space travel in alien environments could accelerate the merging of humanity and technology. We might enhance our bodies to resist radiation, to see in different spectrums of light, or to interface directly with our ships and our tools. The line between human and machine could blur, leading to a new kind of existence we can barely imagine today. This cosmic journey forces us to look inward. Expanding into space isn't an escape from Earth's problems. It's a reason to solve them. To undertake these grand projects, we need to be more united, more collaborative, and more forward-thinking than ever before. The perspective gained from seeing Earth from a distance. The overview effect, described by astronauts, shows us a world without borders, a fragile, beautiful oasis in the dark. It's a powerful reminder that we are all crew members on this one spaceship Earth. The future of humanity is written in the stars. It's a future of incredible challenge, but also of limitless potential. It is a continuation of the story that began when our ancestors first dared to look up at the night sky and wonder. We are the inheritors of that curiosity, and it is our privilege, and perhaps our destiny, to carry that flame of inquiry out into the cosmos. Thank you for joining me on this journey through our potential future. The universe is vast, and the questions are deep, but exploring them together is what makes us human. If you're fascinated by these deep dives into space, time, and our place in it all, make sure to subscribe and hit that notification bell for our weekly explorations. Until next time, keep looking up.